Hi, my name is Minttu Alakuijala, and it's my pleasure to present our paper, Learning Reward Functions for Robotic Manipulation by Observing Humans. Given videos of humans solving various manipulation tasks, we wish to transfer knowledge from this data to a robot arm. This is quite different from the usual imitation learning setting. First, there is a significant visual gap between the human and the robot observations, and a physical gap in dynamics. Second, we don't have access to the demonstrator's actions or even their action space. Prior work has considered the case where there is exact overlap between the tasks demonstrated by humans and the robot tasks, such as the paired video shown on the right. We instead propose to learn a task-agnostic function, estimating a transition time between states, which we call hold for human offline learned distances. We show that this model can serve as a dense reward function for RL and generalizes to many robotic actuators and tasks. We start from a dataset of unlabeled, mixed task human videos and use them to train a distance function using either a regression or a contrastive objective. Once trained, the hold model is fixed and its predictions are used to train RL policies for various goal image conditioned robot tasks. Specifically, the goal of our distance models is to represent functional distance, that is, the number of steps it takes for an expert to reach a state G from a state S. Our first model, hold R, directly regresses this quantity using the time intervals in each video I, each starting step T, and each future step J in the dataset. However, predicting time on an absolute scale is difficult. It's noisy and depends on the speed of the demonstrator. We therefore propose a second method, which defines distances in an embedding space learned using a time contrastive objective. The embeddings for frames within a small temporal window are pushed to be closer together than frames outside a temporal window. We then use the learned distances to define a dense reward for RL. Given a goal image G from the robot, we define reward as the negative distance between the current state and G, transformed such that the distance prediction is 0 at G and never less than 0. We may also augment the reward by adding a sparse success signal. We train separate policies per robot task. We train the distance models on something V2, which features a wide variety of objects, backgrounds, lightings, and tasks. Although distinct tasks are recorded, our method does not make use of these labels. We evaluate our method on 5 simulated robot tasks. In RLV pushing, adding hold rewards significantly accelerates training over using sparse reward only, with hold C slightly outperforming the regression model. However, one limitation is that the distance function pays excessive attention to the arm position, as can be seen in the decreasing distance prediction for the failure case on the bottom right. Without the addition of sparse reward, the policy does not have a way of correcting for this, as is shown by the pink and green curves. It's more difficult to predict distances in the open drawer task, as it's composed of 2 very different motions, first approaching the handle, then pulling it open once there. We find that policy learning gets stuck in a local optimum of matching the arm position in the goal image. However, we can overcome this limitation by defining an intermediate goal image. In this setting, adding hold rewards to the sparse reward again significantly accelerates training. Moreover, hold R alone without any additional reward from the environment forms on par with the true sparse reward. The DVD tasks are much easier and are quickly solved even with only sparse reward. However, our method still outperforms sparse reward and largely matches an oracle reward with knowledge of true object positions. Moreover, hold rewards alone are able to learn the closed drawer task without sparse reward. We also compared the 2 prior approaches able to handle mixed task human videos. R3M proposes a general feature representation, but we consider defining rewards through distances in the learned feature space. Although R3M is trained on the much larger Ego4D dataset and additionally uses language for supervision, hold rewards outperform it on the RLV tasks. We also compare to TCN, which uses a distance function similar to hold C, but differs at the policy learning stage. Whereas our method minimizes distance to a goal image from the robot's observation space, TCN uses 1 human demonstration video and minimizes distance to each of its states in turn. We find this approach to be very sensitive to small differences in the starting states, cropping, and speed of the human video and the robot. Both R3M and TCN also need a sub-goal to solve the drawer task. As our models are trained on real-world data, they have potential to handle the diversity of environment conditions encountered by real robots. We obtained promising distance predictions for real robot demonstrations from bridge data. We'll leave policy training for further work. To conclude, although HOLD is trained entirely on human data, we have shown it to generalize to robot domains and accelerate training on several simulated tasks. Our method is task agnostic and can generalize to unseen tasks through a new goal image. Moreover, goals can be changed to solve longer horizon tasks. In most cases, we found the contrastive objective to outperform direct regression. Finally, we obtained promising distance predictions on real robot data. For more information, see our poster and the project website.